Good morning and welcome everyone. And thanks for joining the Imagery and LiDAR in ArcGIS stream. And this is part of the New Zealand Esri User Conference of 2021. We would have loved to be able to see you all in person, but let's hope we'll be able to do so next year. Today, I'm joined by my colleagues James, Phil and Ted to bring you this session coming from all across the nation. But we're also very lucky to have with us today Andrew from Toitū Te Whenua Land Information New Zealand, Isfan and Mohammed from Plantech Research, and Maurice from Canterbury Regional Council. In today's stream, we will switch between product updates and overviews and some great customer showcases. LiDAR will be an important topic, but we'll also talk about map production from drone images, image management in the cloud, and the new capabilities in ArcGIS Online. And Andrew and Brian will talk about the process behind the LiDAR capture and how Waikato uses the data in their coastal flooding and inundation app. And Morris will show us the importance of aerial imagery that is being captured. And Isfan and Mohammed will show us some of the amazing work that they are doing using AI on multispectral and hyperspectral imagery to map foliar nutrients of kiwi fruits. During the stream, you will be muted, but you can ask questions by using the question mark in the sidebar, and we'll try to answer the questions at the end of the stream around 12:30. And we will have our guest speakers available as well to answer any of your questions. So let's get started. Why do we have a stream dedicated to LiDAR and imagery? And there are a couple of reasons. And we see that imagery has gained massively in importance due to a couple of factors. There's been an explosion of imagery data that is available, satellites that capture images of locations multiple times a day, aerial imagery that keeps getting better, with better resolutions, and of course the LiDAR that will soon cover most of New Zealand. And together with that, the processing capabilities have massively improved as well. And whether that's processing smaller area of interest on your laptop or massive extents using the cloud. And also the advancement in artificial intelligence and machine and deep learning has gone much better, allowing to make better use of all the data that's available. And ArcGIS is a comprehensive imagery system, allowing you to make use of all these advancements. We usually split the system up in 5 capabilities that describe different tasks when working with imagery. And these capabilities are content, image management, map production, analysis and AI, and visualization and exploitation. And I'll go over each of these capabilities and explain what we mean by each of these and how ArcGIS supports them. So starting off with content. ArcGIS supports nearly all forms of content of raster data. It supports a vast amount of formats like TIFF, MRF, JP2, but also scientific formats like NetCDF, HDF, and GRIB. And the data can come from different platforms like satellites, aerial, drone, and even terrestrial. It also supports a variety of modalities like categorical data, multidimensional, 360 images, and also LiDAR. ArcGIS also comes with great content from Living Atlas and partners like the Sentinel and Landsat satellite imagery layers and the world elevation layers and imagery base maps. And some of the new content are the global land cover dataset for 2020 and the 2050 global land cover and vulnerability datasets. And for New Zealand, we have just officially released the New Zealand elevation layer in NZTM for use in 3D applications, and we've added bathymetry to the New Zealand imagery base map. And there's also premium data available, like Maxar and Planet satellite imagery, and NearMap's high-resolution aerial imagery, but more on that later. And traditionally, all this data was stored on hard drives and shipped across when the data needed to be shared. And now we see more cloud storage and image services as a way to share and distribute imagery. So, and all this content needs to be managed. And if you've been using imagery in ArcGIS, you probably know that the Mosaic dataset is the primary data model for managing imagery. Mosaic datasets can be created to reference many types of imagery. These Mosaic datasets can be served as dynamic image services. making all this imagery accessible to the web. And alternatively, the data can also be exported as style packages, which are just visual representations for use as imagery base maps, for example, or exported as static data sets to various file formats, including CRF, which is optimized for storage and further analysis of those data sets in the cloud. Mosaic datasets are extensible as well, and they can be defined as multidimensional, that include parameters and variables for scientific data. And Mosaic datasets can also be persisted as multidimensional CRFs that include transpose options for faster temporal profiles. And these datasets can all be served to ArcGIS Image Server as dynamic or tiled imagery. And new is that you can host your imagery in ArcGIS Online, where it creates either tiled or dynamic image services. And also new is that you can now append to CRF, and that is to support Mosaic datasets growing over time. You can also export a multidimensional Mosaic dataset to NetCDF, which can then enable the datasets to be viewed as voxels. And another data model that is becoming popular is oriented imagery. And this data model provides support for the massive volumes and many modalities for street, drone, 360, and even videos. And this data can be managed using an oriented imagery catalog that can then be made accessible in ArcGIS Pro or in ArcGIS Online or Enterprise. Now let's move to map production. The map production capabilities focus on the tools to generate derived products from imagery, like orthophotos, digital terrain models, and 3D meshes. And depending on the type of sensor and the output required, there's a variety of tools available in ArcGIS Pro and ArcGIS Enterprise. But there are also more focused apps, like Drone2Map, SideScan for ArcGIS, and new is Sure for ArcGIS, that allows you to do specific tasks to create products from input sensor data. And James will take us through the various options with a deeper dive in SideScan for ArcGIS and Sure for ArcGIS later in this stream. Another important capability is analysis. And ArcGIS has an extensive set of capabilities to perform a wide range of image analysis. And this includes things like deep learning, classification, doing spectral analysis, change detection, multidimensional analysis, but also doing things like map algebra and suitability analysis. And these capabilities can be accessed within the ArcGIS Image Analyst extension for ArcGIS Pro. And many are actually available in ArcGIS Pro directly. And you can run all these processes in the image server as well. And they can then be run through APIs or the map viewer. And a lot of this is based on raster functions. And there are over 160 out of the box in ArcGIS at the moment. And these functions can also be chained together to create different processing chains. And this performs all kinds of processing on your imagery. And these are extensible through Python raster functions, where you can make use of NumPy arrays and SciPy, and use those functions then inside ArcGIS. And these functions can be pretty simple, like doing simple calculations, but they can also be more advanced. For example, doing trend analysis and predictions on multidimensional datasets. And these functions are not only available through ArcGIS Pro and ArcGIS Enterprise with Image Server, but now also through ArcGIS Online. And we'll see some examples of that later on. And I wanted to highlight a couple of the new tools that have been released that are designed and built to make analysis on imagery easier and faster. The change detection wizard was introduced to guide you through the process of change detection. And this can be change detection on 2 datasets or on a larger time series of datasets like the multidimensional Mosaic dataset or CRF. And suitability is used to identify the best location for an activity or find areas to preserve based on many input parameters like slope, distance to streams, and so on. And the suitability modeler in ArcGIS Pro allows you to do those analyses in an interactive and exploratory way by, for example, changing the weights of each input parameter and dynamically see the results of those changes on maps and charts. And Esri is also working to make machine learning and deep learning more approachable by introducing new tools and workflows for doing those types of analysis inside of ArcGIS. They're also releasing more and more pre-trained models that can be used for machine learning and deep learning, And these models are all available in ArcGIS Living Atlas and are also being used in tools and solutions like the 3D basemap solution that we'll look at a little later. The final capability of imagery in ArcGIS is visualization and exploitation, and this includes a wide range of tools to enable human interpretation of the imagery and include the many interfaces to interact with imagery and the resulting information products. And just to highlight a few, in ArcGIS Pro, for example, you can work with stereo imagery, motion imagery, usually coming from drones, and you can also use oblique imagery. And we'll also show you how you can visualize and exploit LiDAR point clouds in both ArcGIS Pro and ArcGIS Online or Enterprise. And one of the types that I mentioned before that is getting more traction is oriented imagery, which you could describe as very high oblique imagery. And for ArcGIS Pro, you can download a toolbox and an add-in that allows you to manage and explore oriented imagery catalogs. So you can see the location of the images, the field of view, and quickly navigate to the image that covers the area of interest. And for the web, you can use one of the example apps or the JavaScript API to build your own web applications to exploit oriented imagery. And new in the latest release of ArcGIS Online is the Oriented Imagery widget for Experience Builder. And this allows you to quickly configure a web application to make your vast collection of oriented imagery available to other users. So this was a brief overview of the capabilities in ArcGIS when it comes to imagery. We'll now look into map production and the various tools available for that. So I'll hand it over to James.
Awesome. Thanks for that great intro, Baldwin. Looks like our slide deck's disappeared. As Baldwin mentioned earlier, there are a number of different map production tools to suit your own needs and workflows. Oh, here we go. For example, in the next slide, ArcGIS Pro and its Author Mapper tool is a great choice for bringing in scan film, as you can see on the left-hand side there, as well as aerial or satellite imagery as well. It is a professional tool that has a few more levers you can pull in order to make corrections to imagery, for example. Bear in mind that you can only derive orthomosaics and elevation models from that product. The same, I guess, limited outputs can be generated from AutoMaker, which is an image server capability of ArcGIS Enterprise. Here you can use the large amount of computing power to process large image collections within your own environment. I guess that's an important factor there. However, today I will largely focus on the two drone-specific map production tools that are ArcGIS Drones-Map and SiteScan for ArcGIS. So I'll take a quick look at those now. So ArcGIS Drones-Map is a desktop-based drone-specific map production tool that allows you to create products such as dynamic and DSM orthomosaics, digital elevation products, as well as 3D point clouds and 3D meshes as well. You can also perform some basic analysis and share products directly to ArcGIS Online and Enterprise. Drones-Map is designed to be intuitive and streamlined to enable you to go from the field to actionable products as quickly as possible, really. As you can see from the slide, Drones-Map integrates directly into ArcGIS Pro, allowing for more advanced image management by using the Mosaic dataset, as well as access to a larger catalog of imagery analysis tools. On the next slide, I want to talk about SiteScan for ArcGIS. This is also a drone-specific map production tool. You can also generate the same 2D and 3D outputs as Drones-Map. The difference is that SiteScan is a fully SaaS-based product. That means that all of your imagery products that are both stored and processed in the cloud. This allows for faster processing times and an unlimited amount of image storage. There are also additional administration tools to manage larger drone operations, for example, tracking pilot and drone operations, as well as documentation on those activities. Also, there is things such as report generation in an automatic fashion as well. Finally, you can directly share those map products you generate with ArcGIS Online, Enterprise, as well as the Autodesk BIM 360 tool as well. In the next slide, I just want to quickly leave you with this before I leave SiteScan, and that is highlighting the SiteScan Flight for ArcGIS. The Flight app is focused on a streamlined workflow to feed imagery into the downstream SiteScan processing. This app is also available to our customers processing in DroneSmap, AutoMapping, as well as AutoMaker as well. The advanced flight planning features in SiteScan help to ensure quality data collection and accurate outputs as well. There is also a direct integration to interface with ArcGIS Quick Capture, using drones to make aerial observations and capture real-time data points over the critical or hard to reach sites, for example. You can also record video files with this SiteScan Flight. It captures all the relevant metadata required to feed directly into the video multiplexer inside ArcGIS Pro for motion video tools. That's part of the Image Analyst extension. So on the next slide, I just want to quickly talk about why might you choose DroneSmap versus SiteScan? It's a question we get asked quite often. So really it comes down to the type of work or the type of mission you're working on. So at the bottom left there, what if I'm working offline or I'm just a small scale operation? It all starts with the planning capturing with that SiteScan Flight tool that can work online and offline. Then it would probably move to ArcGIS DroneSmap at the bottom there. As it's a desktop-based application, I can take it with me out into the field on my laptop and actually start to process that imagery directly from the field in that offline scenario. From there, it's just a matter of publishing up to ArcGIS Online or Enterprise. For maybe larger storage requirements, so you're capturing a lot of drone imagery, that's where you might want to start moving towards SiteScan Manager. Since it is, I guess, cloud-based and it allows you to fully not worry about any of the imagery that you're storing or capturing, it really allows you to take advantage of that cloud processing and storage. Same again, sharing out to ArcGIS Online or Enterprise. So really it's a matter of scale as well as use cases. On the next slide, I just want to touch on Shore, which Baldovan mentioned earlier. Shore is the newest addition to Esri's imagery map production tools. You can think of Shore as a new image processing engine that can automatically process imagery input with precise orientation data and or LiDAR data as well to generate really high quality outputs. These outputs can include what we call true orthomosaics, as another name for a DSM orthomosaic. This is a reference to placing all of the imagery, including rooftops, in the correct horizontal position, as well as highly accurate and realistic 3D meshes and point clouds. Here in this demo, we can see some of the outputs from Shore's processing engine that is currently being used in SiteScan. The engine will soon be included in DroneSmap in the release later this year. Finally, the Shore engine will also be made available in other ArcGIS products, as well as its own standalone application in the coming months and years as the integration becomes tighter. As you can see, the 3D meshes here are really quite high quality. It also shows that Esri is taking 3D meshes a bit more seriously and are heading in the direction of turning meshes from things that are nice to look at to actual 3D GIS features. Having high quality meshes is a massive step in that direction, so stay tuned for more in this exciting 3D space. And with that, I will hand back to Baldovan.
Yeah, thank you, James. I think that was a great overview of the map production capabilities in ArcGIS, and especially as we see drones becoming a very big source of data. And another big source of data is the National Elevation Program. And we've heard a bit about the capture planning during the plenary of the New Zealand Esri User Conference from Andrew. And he will now give us a more detailed overview and a peek behind the scenes of what is happening before this data is released to ensure the data quality. And after that, Brian will also give us an example of how this data can be used to manage coastal flooding and inundation.
Kia ora, Andrew Farrell from Toitū Te Whenua Land Information here. I'm going to give a bit more of an update on the National Elevation Program, and then Brian Clement is going to come in and talk about one of the tools that Waikato Regional Council have developed using LiDAR. So today, I'm just going to go through the program and a few more bits of information that we probably didn't cover in the plenary last week. So we are talking airborne LiDAR here. We're not talking from the ground LiDAR, we're talking airborne LiDAR, and it's capturing over vast quantities in New Zealand. Again, just to reaffirm you that this is actually a partnership model. So this is central and local government working together to get this information out there for people. So big pat on the back for all the local regional councils, etc., and TAs. A lot of the effort is coming from them. So this data, even though it comes out available on the LINZ data service, etc., they're the ones that need to be patted on the back for a lot of this. So this includes the funding, the planning, the procurement process, and then the big one, which is going to be the realizing the benefits of this data. We were lucky enough to use the PGF as a way to really enable a step change in our ability to capture some data. So what that step change is if you look at this graphic, you've got our current state of LiDAR available in New Zealand as of today, and in the right, what it's going to look like at the end within 2024. And this is 80% of the country, and this is a fantastic jump in data. Now you'll notice some gaps, and people always notice these. At the moment, these are areas we will continue to work on these areas and try and find mechanisms to get data in those areas. Like a lot of things, it comes down to money and timing. So we'll keep working on that and see where we get to. Keep an eye on elevationaotearoa.co.nz because this is where we will be putting updates of data available and information about data that's coming, which is quite important to a lot of people understand when they're planning their work. When's the LiDAR in that area likely to be coming? So National Elevation Program will result in LiDAR-based DEM, which is the bare earth model, DSMs, which is the surface model, and also point clouds. Again, Creative Commons data, so it'll be able to be used by councils, government, private industry, individuals alike. There won't be any constraint on that. And we're trying to ensure that this is nationally consistent. Vertical datums are the same, etc. So keeping it consistent so you can move from one region to the other easily. Okay, just a reminder of people. So this is essentially what we'll get from the bare earth model. So it's a representation of the ground with none of the surface features on. So that's the DEM. The DSM is when you start to bring those surface features back onto the data set. So that is the vegetation, the buildings and such. And obviously the point clouds. The point clouds allow a lot of other bits of work to be done from them, and these are classified into different feature classes. So for example, vegetation, buildings, water, etc. are all classified differently so that people can choose what they wanted to use and how they use it. So QC, this is probably the bit we really want to get across, is that we are, and when I say we, it's the councils and LINZ have put a lot of effort into ensuring that this data is consistent across the country. And so again, this is a collaboration between LINZ and the councils are doing a certain element of QC, and LINZ is doing some QC as well. So we just want to give a little rough coverage of what happens there so that you can a bit more confidence in the data that a lot of the issues will have gone in the data by the time we get there. So from the council point of view, they use ArcGIS Online Web Scene to view the data, and this is something that they've built in collaboration together, and it allows them to all have this kind of the same process from region to region. The DEMS and the DSM image and elevation services as well. So from the point cloud scene layers, they use this to check the classifications. So they'll make sure that what is the ground is correctly classified as ground, buildings, vegetation, water, etc. They're all classified in the right way so that we're not seeing errors in the data where things that should be classified as one thing are classified in the other. We want the data to be usable from day one when people get it. So the QC checks, from a council point of view, they've got some really good local knowledge, and so there's certain things that are more topical in certain regions. So, for example, vegetation and crops are something that they want to make sure are being removed from the bare earth models, the DEMS. And there's an example at the top here where if they aren't, it does have an effect on the way the data is used. Making sure that bridges are removed has a big effect in terms of if we're doing hydrology and you're not able to, the bridges aren't removed, you want to see where the water is going to flow correctly. Things like snow on the ground, flooding, things are hydro-flattened, buildings are showing where they should be and have been removed from certain products when we get down to the bare earth, etc. So from a LINS side of things, we QC to ensure that the final deliveries conform to the national base specification. And you can actually get that specification online, and it's a list of lots of different things. So there's probably well over 50 checks that are done on the data to ensure that it's fit for purpose and it conforms to what we wanted. So I'm going to give you some examples here of mainly errors, but this should be really positive. Flying companies are doing a really good job, but these are the kind of things we look for. So this is an example of an error in hydroflattening where the lake was actually hydroflattened about 50 meters higher than it actually was, and obviously that would have massive effects on using the data. Here's an example of artifacts in the DEM where there was a spike in the DEM, and it's actually part of a building that should have been removed in the bare earth model, but it's just a remnant from the DSM. So keeping an eye out for that stuff, making sure that we understand that it all needs to be removed. Here's another example of intensities where they haven't been normalized across the whole data set. And so to use the intensity values, you need them normalized across the whole data set. And it just makes life a lot easier and makes you able to use the set in totality a lot better. And a couple of other examples: interpolation artifacts in the DEM, incorrect georeferencing where the one of our tiles ended up in Europe, tile edge artifacts down the bottom, and obviously gaps in first returns where you shouldn't really have gaps like that. So ensuring that we're checking on these so that the data is in the best condition it is when we release it. But QC is one thing, and I think the value of the QC means that people are not having to spend as much time correcting the data before they use it, and that's valuable. But the value comes from people actually using the data, and this is something that we're really big on. We want people to use the data, but more importantly, we want you to tell us how you're using the data. Councils want to know, LINS wants to know. It's just an important thing so that we can show the value of it going forward. So there's many uses for this data, and this is just a throw on the board of some of the examples. It's used in engineering, agriculture, water storage, urban design. You know, I could say them all, but they're right in front of you. Most of you here will know the value of data and how it can be used. So I'm just going to show you some examples of how people have used it. So relative elevation model. So this is a relative elevation in the Manawatu River, and it just really shows the value of LiDAR for identifying how the ground was and in comparison to the river, how it is in comparison to the river. Slope maps. Here's an example of somebody who's created slope maps for determining the steepness of ground in certain areas. Feature extraction. This is a picture of buildings being able to be extracted from it, vegetation being extracted from the LiDAR. Identifying fault lines. Now, if you can't see the fault line, that's pretty clear to me, but it's really good for visualizing things like fault lines and that. This one's a lava dome of Mare Island, and I think these are different lava domes. They progressively get younger, I think it is, and it's just a fantastic way of showing information. Here's a detailed hillshade of near the Buller River, near the Westport, and just shows you the lie of the land and a really detailed look at the land. And obviously on Elevation Aotearoa, we have some case studies. we want more of these. We want you to help us with these. So we're really keen to get some of your stories and to get your stories up on here. And so Brian Clements is now going to go over one of the examples that we have up here of one of our use stories, and he will go through that. Thank you.
This case study highlights LiDAR being used to support a coastal inundation tool that has been in public use for a couple of years now. The tool gives users the ability to visualize the impacts of coastal flooding, which is a significant hazard across Waikato's lower-lying coastal areas. Coastal flooding poses serious risk to property, business, and sometimes to human life. Interest in the tool has come from the likes of the insurance industry, property owners, and real estate industry. Local council hazards management people, and other general public interest. There are various contributing factors to coastal flooding, like high tide levels, storm surges, tsunami, and sea level rise as a result of climate change. The tool includes supporting links that provide a lot more information about these factors. Rather than try to predict when flooding will occur, the tool's purpose is to show which areas of land are prone to flooding as sea level rises. The tool treats the ocean like a bathtub, so a water surface that rises evenly, filling the lower parts first. This is the effect that is demonstrated on the lower-lying areas of land, showing the land that would be flooded as the sea level rises above certain heights. LiDAR provides one critical component of the tool. It is used to produce a detailed digital elevation model, or DEM, of coastal onshore areas. This provides an accurate 3D map of the terrain, including things like low-lying areas, drainage channels, and high points. The tool also brings together years of historical sea level data, using local tidal records to understand base sea levels at certain locations around the region. In the tool, the user can zoom to a coastal area of interest, then simply use the sea level slider to visualize a particular rise in sea level. Two types of flooding are shown. Blue shows land areas flooded directly by water flows such as via the beach or waterways, and green shows areas lower than the chosen water level that are likely to be flooded but without a direct flow path to the sea. By late 2022, as part of the LINZ Provincial Growth Fund initiative, the new LiDAR collection for the Waikato region will be available. One of the many applications of these data will be an update and extension of the coastal inundation model, providing an even more detailed and accurate tool than currently exists.
Yeah, so thank you, Andrew and Brian, for these stories. And it's pretty amazing, right? First of all, what it takes to capture and deliver all this data, but also very interesting to see the usage you can get from it. And personally, I love just going over the different visualizations of this LiDAR and finding all these things, features in the landscape that you can't see using aerial imagery. And remember, if you have any questions for Andrew or Brian, please drop them in the questions pane. Andrew will probably be here to answer them live, and otherwise we'll get back to them and send the answers out to you in our resources document. So with all this LiDAR coming in and becoming available, we will now show how the actual LiDAR point clouds can be used in ArcGIS. And one of the ways of using this data is to extract information from it using the 3D basemap solution created by Esri. And we will start with Phil, who can tell us more about this solution and how you can use it to start building your own digital twin.
Thanks, Badaveen. So now I'd like to introduce you to the 3D basemap solution. This is an ArcGIS Pro project you can download from ArcGIS Solutions. The template has a series of tasks to follow that allow you to build a 3D basemap from LiDAR data. I'll just jump to the next slide. The first task is an introduction to the solution and provides you with some sample data to trial using the template. And the next task guides you through importing your data and running tools to create ground surfaces, extract 3D buildings, trees, bridges, power lines, and even allows you to import data from underground pipe networks. And then finally, you can share, you can publish your base map to a web scene and share within your organization. Next one. So some use cases for the 3D base map can include importing a CAD drawing of proposed buildings into your scene, so you can better visualize the impacts planned development may have on the surrounding area. For example, performing view shed or shadow casting analysis, you can see in the video on the right. One thing I found helpful when I was using the solution was that when I was creating the building footprints, to save time, I was able to bring in the LINS building outline layer. Although if you're working in an area of recent development and there's no existing data in your area of interest, the template can integrate deep learning to extract the building footprints from the DSM. And that's an example in the video on the right as well. So yeah, this was just a quick intro into the 3D base map solution. And now James will take you through some of the examples of the LiDAR used to create 3D base map of Westport.
Awesome. Thanks for that great intro to the base map solution, Phil. I'd like to first take you through a quick tour of some of the LiDAR tools available to you. I have a subset here of the Westport LiDAR data here in ArcGIS Pro as a last data set. When I activate that layer in my contents pane, a new set of tools appear. Since this LiDAR has been classified already, I can go ahead and symbolize by the class of that LiDAR, as you can see here. Now I can gain a good understanding of where our buildings are relative to our trees. And in the data tab, there are handy measurement tools and tools to manage your last data set as well. Finally, in the classification tab, there are tools to help reclassify your data. We can use this handy new profile tool to take a snapshot of our point data, which can help us to reclassify incorrect points. Here in this 3D scene, we now have the LiDAR hosted as a point cloud. Oh, sorry. First, you can filter down to just the data you want to see, like you can see filtering down just the trees there. And now we can just see our tree points in the Pro there. Now we jump to the 3D scene, and we can see the LiDAR hosted as a point cloud scene layer, which quickly renders over the web using the latest I3S standards. All of the same attributes apply, so we can symbolize and filter the same way we would in Pro. Here we have that same class rendering, but we also have a colorized point cloud. The point cloud using Pro, this is the point cloud we generated using Pro, sorry. This gives us, I guess, a more realistic looking model of Westport, which actually looks quite great. The point cloud is nice to look at, however, we actually want some usable GIS features from it. This is where the features we generated using that 3D base map solution come in. Here we have that 3D object scene layer of buildings pulled directly from the Westport LiDAR using the 3D base map solution. Notice that even the unique roof forms are pulled out. And clicking on the buildings themselves, you can see the attribute information, such as the building and eave height, and the roof form as well. So being a GIS feature means we can attach other attribute information, such as location or anything else we would like to join as well. Other features extracted are vegetation with varying tree models based on the height and attributes of the trees, such as the radius as well. We also have bridge features extracted from the LiDAR with a representative model in its place there. So there you have it. Using the 3D base map solution and LiDAR tools in ArcGIS Pro, we've now extracted a whole town's worth of GIS data from LiDAR. This new 3D data is going to be valuable for all centres to aid in their planning, modelling, and overall understanding of their towns. With that, I hand back to Boudewijn.
Yeah, that's a great example of how data technology and advancements in machine learning can come together to create engaging information products. So next, I would like to switch to imagery management, and more specifically, when using the cloud to store the imagery. Because at the New Zealand Esri User Conference, I talked about two general ways imagery can be published. It's either curator managed, where a person or a group of people manage the imagery and make it accessible. The other method is the user managed or hosted way of publishing, where you can use the portal in ArcGIS Enterprise to publish your imagery. And this makes publishing of imagery much easier and faster for users in the same way that they can create feature layers from the portal. We'll look later at this workflow that is now available in ArcGIS Online as well, that allows for publishing the imagery layers. But both options also allow you to use imagery that is stored in the cloud. So let's dive a little deeper in managing and then publishing imagery when using the cloud storage, or specifically object storage like Amazon S3 or Azure Blob Storage. First, why would you actually use this type of storage? Well, cloud storage for imagery is being used more and more, and that is because it has some benefits over local hard drives and shared file locations. And the main benefits is that it's relatively inexpensive. Many machines can simultaneously and efficiently access the same storage, and it's nearly unlimited in size. So object storage can be many, many petabytes. One downside can be a higher latency, and that is especially the case if you've got clients that make thousands and thousands of requests, for example, to read the rasters. And performance is an important factor. So ArcGIS optimizes performance by limiting the number of requests and caching when needed. But the file format and compression is also important. And when data is received from data providers, often it is a simple untiled TIFF or GeoTIFF without any pyramids or compression. And this is a relatively inefficient storage format when you want to access those files, as for example, an image service. There are better options like tiled TIFF or GeoTIFF that are more optimized formats. And you can choose to add compression to reduce file size and build pyramids for faster access at the smaller scales. Another option is the MRF format, and that is developed by NASA for optimized access for both read and write actions. And it's styled and uses pyramids, and it also supports the LURC compression, and that allows for controlled lossy compression, which is particularly useful for elevation data. And once you've decided on a format and compression, you may need to convert and upload your data to the cloud. So there are a few ways to convert that imagery. One is using the export or copy raster workflow in ArcGIS Pro. Another is using the GDAL translator library. And Esri has also developed a set of tools called Optimized Rasters that is available on GitHub. And this set of tools uses GDAL in the backend and allows you to convert rasters into different formats with settings for compression, resampling methods, and pyramids. This tool also allows you to directly upload imagery to the cloud, and it allows you to create raster proxies, but more on those later. And you can also use third-party apps or use the command line interfaces, the CLIs from the likes of Amazon and Azure to upload your imagery. And once the data is uploaded to the cloud, you need ways to access it, right? So there are a couple of ways to access the files in object stores. And one is using the VSI file handlers, which are basically URLs to the files. You can also use raster proxies. And these raster proxies are very small XML files that hold information about the actual cloud storage location. And these raster proxies can be used similar to the original files and can, for example, be added to a Mosaic dataset. And since ArcGIS Pro 2.7, you can also create a so-called .acs connection file. That's an ArcGIS Cloud Storage connection. And this is similar to how you can register a database connection, and it allows you to access the data from the catalog pane. And the location and references will show up in the catalog just like a folder. And you again, you can work with the files as if they're local and add them to Mosaic datasets. In ArcGIS Enterprise, you can set up a data store connection, either in the ArcGIS Server Manager, or since ArcGIS Enterprise 10.7, you can create data store connections from the content page in the portal. And these data store connections allow you to connect to a specific cloud store. And to make the imagery even more accessible, you'll probably want to publish the data as an image service. And using the user managed workflow, you can go to the ArcGIS Enterprise portal, and if image server is installed, you can select to create an imagery layer. And you get a wizard that guides you through all the steps, and one of those steps is to select the imagery. And you can upload imagery from a local folder or use the data store connection to select folders or images that are in the cloud store. When you're publishing from ArcGIS Pro, you can publish to ArcGIS Enterprise with image server or to a standalone image server. If you have used an .acs connection to access the images in ArcGIS Pro, you either need to have a data store connection with the same credentials configured, or the server needs to be able to access the ACS connection file, similar to when using a database connection. And if you use raster proxies, you'll want to copy the raster proxies to a location that is accessible to ArcGIS server. And this doesn't take up a whole lot of space, as the proxies are really small. And if the cloud storage isn't publicly accessible, you also need to configure the server so it can access the cloud store through, for example, the environment settings on the server. But once that's all set up, you can just right-click the Mosaic dataset or raster that you want to publish and configure the settings for the image server and then publish it so it's available to other users. So this was a quick overview of the things you need to be aware of when using imagery in the cloud. And if you're interested in using this method or already use a cloud store but would like to know more about the file formats, cloud connections, and so on, there's some good documentation available. We'll add the links to this workflow and best practices in the resource document that we'll make available to you after this session. And one big source of imagery that needs to be managed is aerial imagery. And we all use the final product as an imagery base map, for example. But Maurice Wills will give us insight in what's happening behind the scene of the capture, but also how this and all the historic imagery is being used at Environment Canterbury and their partners.
Kia ora, Atamarie. My name is Maurice Wills. I work at Environment Canterbury as a Geospatial Technical Lead, looking after Canterbury Maps and the aerial imagery acquisition and delivery for the Canterbury Aerial Imagery Consortium, which makes up of the Regional Council, Environment Canterbury, as well as the territorial authorities and LINZ as well as a partner. Why is imagery so important? I'd like to quote here author Philip Roth: "Seeing is believing, and believing is knowing, and knowing beats unknowing and the unknown." Sink in, I guess. There's quite a bit in terms of that goes into acquiring aerial photographs. Currently, we tender for the work, and we are seeing that both at the Regional Council and the territorial authorities, we are needing this data more and more with a higher frequency of capture. Just to show you how behind the scenes look, the camera sits in a stabilizer in the aircraft, and some cameras take a continuous stream of images like you would creating a panorama photo on your mobile phone, while other cameras take individual snaps that the provider then seam lines together to make one large image over the region. Careful flight planning is needed from the providers over large areas to get enough overlap. And ground control work to geofence the image into the right geographic space. And obviously, hilly or mountainous terrains are a lot more difficult to capture and geofence than the plains area of the Canterbury region. The sun angle makes a difference as well in terms of the shadow effects. We want to minimize shadows, so summer is obviously the best time to capture photographs, so the sun is at the 12 o'clock or nadir. As well as that, you know, the flights need clear weather, being cloud free, and then, you know, agricultural farm fires as well can hide areas underneath in terms of the smoke, and they aren't able to fly in high winds either. We capture two different resolutions and a specification. In the urban area, we have a 7.5 centimeter pixel size, or GSD, ground sample distance, so we can spot, you know, more features that are in the built environment. In the rural areas, we typically capture between 20 and 30 centimeter. That's because we want to cover a bigger area. So a lot more flying and a lot more photos. So this specification, just to get the amount of data in. delivery of the imagery comes in as georeference TIFF files, a raw image format, and we ask the providers to tile it in the LINS tiling scheme. We capture in RGBI, red, green, blue, being the true color viewable bands, and in the near infrared band as well. I'll show you an example of that later. Flying heights, just for people to get a background, is about 5,700 meters to 1,400 meters. And then if you're looking for specifications, LINS have a couple of good specifications on their website. The full imagery specification written a few years ago, and then also an emergency management one for kind of quick capture quick contracted pieces of work. Different spatial resolutions will mean different horizontal accuracies as well. And we've got this nice table again in that LINS specification document. A 0.1 meter spatial resolution will result in roughly about 0.3 meter horizontal accuracy. Going up to obviously 40 centimeter will be a lot less horizontal accuracy in terms of about 3 meters. Users can access this data set in a few ways. So currently, and in the past, we've supplied it as tiled map services from our imagery server on the left-hand side here, and we can see the 24 levels of detail on the bottom left there. And on the right-hand side, we also supply via an image service. That means that's the raw GeoTIFFs. It takes a bit longer to draw, but obviously that's higher quality, and we swap out when users need to print out data, high resolution imagery, we swap it out for the image service. The public can access via Canterbury Maps viewer, and through the Basemap gallery here, we've got all the historics and the latest imagery in there, and we kind of group it, the historics, to 5-year blocks. In our property-centric application, Canterbury Maps Property Search, we've created this time slide functionality, so users can just toggle between different historic imagery. You can see here an example of the growth of Rolleston. And just to show you this example of rural Canterbury, captured in the infrared bands, we can see here in infrared the kind of the water features. The irrigation ponds are a lot more clear; they come through clear, and the high vegetation areas, forestry blocks, they're a lot darker, and you can spot those a lot more easily. Imagery is also helpful to record large, civil defence emergencies. And we can see here the after effects of the Canterbury earthquake, Christchurch earthquake rather. A lot of damage to the CBD and all of Christchurch. Every emergency comes with its own different challenges. So here is the Kaikoura earthquakes, which shifted a lot of mountainside, lots of hill slides, creating artificial dams, and we had to monitor those in terms of built up water in the high country. And whole communities can be cut off in terms of Kaikoura. State Highway 1, north and south of Kaikoura being cut off. Historic imagery lets us travel back in time to measure the biodiversity and habitat loss. You can see here just how much wetlands has been lost around the rivers. And we can have real conversations with the communities on risk and resiliency planning for what will become more severe weather events as the climate changes. We can see here air photos being used in conjunction the oblique photographs that we get through the civil defence emergency. Typically we get the obliques within the first 24 hours, and then the low-level aerial imagery we aren't able to get until about 48 to 72 hours after the height of the flood. but it all complements together. This is obviously the recent look at the flooding of May 2021 in the flood imagery register that we have for the old obliques, and the same area flooded, and I can see that in 1963 similar size flooding occurred. Here, looking at the Rangitata flood of 2019, we can see here the flood imagery breaking out the banks in the southern Rangitata branch, but we can see in the aerial photos it used to flow down this area, and the floodways are clearly mapped, and they basically match up with the flood event itself. So infrastructure like power lines and state highways, typically the design should be a lot stronger over these kind of floodway areas to be able to cope with these events. Here is an example of the Port Hills forest, and unfortunately there was a big Port Hills fire, and we can see that if we again look at today's photo, how much forest was lost to that event. So there's a few examples of the imagery collections at Environment Canterbury. And where to next? Obviously the historic imagery helps us plan for the future, but for the future being more sophisticated, supplementing the aerial imagery with satellite imagery, which is higher frequency. Maybe we've got a subscription for daily imagery, oblique imagery where it's needed, rapid aerial imagery for civil defence events, continuing the regional imagery program itself, and then getting into newer technologies like 3D mesh imagery data. And we look forward to using our aerial imagery with the 1 metre digital elevation model across Canterbury region through the PGF LiDAR project with LINS. And we'd like to move to delivering the imagery via software as a service on ArcGIS Online, so it's scalable for everyone. And we've done a lot of proof of concepts with Geo AI, so I'll take you through a couple of examples of that. Here's an example of 3D mesh of the Christchurch CBD, 5 centimetre pixels. This will let GIS open up the kind of applications into urban development. And in the 3D mesh, it becomes more of a real world example, a digital twin type functionality. Some quick proof of concepts using Geo AI techniques. Here we've got an example of wetlands that have been lost, so using the imagery to identify and monitor wetlands. Gorse and broom, just where they're prevalent. Here we've got a shot of Banks Peninsula here, and we've lifted out data from the imagery itself. You can see there quite easily set to see in the high resolution aerial imagery what it looks like from above. We've been also looking at winter crop, so identifying paddocks that have been sown into winter crop, check for elevated risk as per our freshwater policy, and feed into prioritisation of what we monitor. So thank you very much for listening today, and thank you for Eagle and Buddhaman for letting me the opportunity to speak today to you. Any questions? Fire them through. Thank you very much. Bye.
Yeah, so thanks, Morris. That was a great overview, right? But also what he doesn't highlight is all the effort that goes into making all this imagery available to basically the public. Morris mentioned using satellite imagery just briefly there. And that's the next topic I want to talk about. And that is the premium imagery partners. And that's the imagery partners that we have, and for that we've asked Ted, our colleague, to give an overview of the different options that are available.
Sure thing. Thanks for that, Badabane, and hello everyone. Thanks for joining us today. Brief introduction to myself. I'm a GIS account manager at Eagle Technology. I represent one of the partner offerings, but today I'm going to touch on all three of the key ones for you. and sort of go through everything at a high level for you. Just a heads up, this will be a very quick run through as we've got a lot of stuff to cover today. So if you're interested in any further information, please just let us know in the comments or in the chat, and we can follow up with you after this call. So yeah, let's start off with a summary of the various partners and what they have available. Jump to that next slide, please, Badavane. Cool. So our three main imagery, premium imagery partners are Nearmap, Maxar, and Planet. Most of them you'll hopefully be familiar with already, but if you're not, Nearmap is the one we'll start with. That's a fixed wing imagery provider, so it's flown over the 14 main areas across New Zealand, covering about 74% of the population. And so in terms of currency for those areas, Auckland, Hamilton, Wellington, and Christchurch are covered twice a year, and the other main centres are covered annually. As it's fixed wing, the resolution is really high, so it's around that 6 centimetre mark, and is actually better in some cases. In terms of bands, it's 3-band RGB, and the archive's been built up since 2017. The other two providers, Maxar and Planet, are both satellite imagery providers, and they orbit. They have satellites orbiting globally, so the coverage is global. In terms of frequency, Maxar is generally once to twice annually, although you can actually task it for more frequent revisits. And there are more satellites that will be launched soon, so that will bump up the currency of capture there. Planet's near daily, so they have a fleet of 140 satellites constantly capturing imagery, although with cloud coverage, this sometimes hinders the daily capture. In terms of the resolution of those two offerings, Maxar is in the 30 to 50 centimetre range for the core imagery, although you can actually bump it up to 15 centimetres and for some selected images where the quality is high enough. And for Planet, there's two resolutions on offer there mainly, which is 3 metre for Planet scope, which is the daily capture, or 50 centimetre for the SkySat, which you task for a specific area. Coverage for those bands, both Maxar and Planet go beyond RGB. They have near infrared bands available, as well as multispectral and shortwave infrared through Maxar. And those archives are also quite big as well. You can see there for Maxar dates back to 2000, and Planet back to 2009. The next part of the partner content summary, just going to touch briefly on commercials and the consumption methods. Each of the providers here, they all have self-service imagery through browser platforms. So you've got the Nearmap browser, you've got Secure Watch from Maxar, as well as Planet Explorer. And using these platforms, you can stream imagery at your leisure. You can download areas, and you can also integrate into other systems using web services. So you've got WMS there, WMTS, and there are a variety of other OGC compliant methods you can use. And there, you can also use APIs, and there are plugins available. You can see there for Maxar and Planet. There's the add-ins for desktop. On the commercials, yeah, you generally subscribe to an annual subscription. It might be a data model, so you consume data as you go, and then that churns through. And then there are various. You can actually order archive imagery through Maxar. And you can set up tasking, and there are base maps available both through Planet and Maxar, particularly around that daily capture of imagery there. Now we're going to jump across and touch briefly on some use cases, some common use cases we're seeing out there already. Although if you have other applications you're thinking of, by all means go for it. Starting with Nearmap, focusing on the urban areas specifically. Nearmap imagery is really good to supplement that LINS imagery capture, and generally with those urban centres that it's captured biannually, so you can there's a higher cadence there. Looking across some of these industries here where you need to sort of check in regularly and see what's happening in the urban areas, industries such as architecture, engineering, and construction, site monitoring. If you're looking at transport and logistics, you might be assessing roads and railway lines for maintenance. And also property insurance, you might be looking at where new properties and buildings are popping up and going through the insurance claims and those sorts of things. And a few other examples there as well. You can see urban planning, you might see urban sprawl and development. And this is just a quick snippet of Hobsonville in Auckland, and you can see how the land is changing from 1 month to the next throughout 2020 and 2021. Now moving over to Maxar. So the main use cases of Maxar we're seeing at the moment mainly focus on the research and scientific analysis, and that generally comes down to the fact that this imagery goes beyond the urban centres, so it's global and it captures in rural areas, and the fact that there are more bands available for analysis. You're looking at the near infrareds, you're looking at multispectral and shortwave infrared. So having that data available is really valuable for people in these industries. Also looking at agriculture and horticulture, making use of these bands. Again, you might be looking at the near infrared to visualize crop health and assessing seasonal variation of the of your crops. Also for disaster response, MAXAR do set up emergency taskings when events happen, and satellites will try to capture the area, hopefully cloud free, and so it can be used. And if it is successfully captured, they make it available through the Open Data program, and you can leverage that. And here's just a quick example of the south coast of Wellington where a kayaker went missing earlier this year, and so some imagery was captured. And finally, looking at Planet. And so Planet, the main value of Planet is obviously that near daily capture. And so for the super high cadence and quick turnaround, agriculture and forestry is one of the main focuses for Planet use. Working from planning through to harvest through agriculture. Forestry, you're looking at harvest markup mapping, wind throw, and then also investigating crop health. And finally, emergency management. You can see there you've got Pigeon Valley, and you can assess sort of the smoke and burn areas from one day to the next. And then at the top there, you have some agriculture use in the Hawke's Bay. Just to wrap up, I'm just going to show you a couple of sample images so you can assess the resolution. These images here, we'll send out links for them after this webinar, along with some other content, some resources on the premium imagery offerings. But yeah, that should hopefully give you an overview of the different resolutions that are available for those offerings. And that's pretty much it. If you do have any more questions, please just do get in touch with us. And like I mentioned, there'll be a link to the other Esri imagery partner webinar we did previously that should go into more detail than I've been able to cover today. And with that, I will hand back to the rest of the team. I think Phil's up next, so over to you, Phil. Thanks, everyone.
Yeah, I'll jump in first before we go to Phil. Thanks, Ted. So that's an overview of the other imagery that's available, coming from our eyes in the sky. And this imagery, a great way to publish this imagery is using ArcGIS Image for ArcGIS Online, and that's a new kid on the block. And Phil will give us an overview of how you can use ArcGIS Image for ArcGIS Online to publish imagery quickly and make it available to other users. So take it away, Phil.
Cheers, Badavin. So yeah, introducing ArcGIS Image for ArcGIS Online. It says software as a service offering that allows you to manage, visualize, and analyze your imagery data without the need for infrastructure. You're able to upload your imagery into ArcGIS Online via web browser or the associated API. It introduces two new types of imagery layers, a tiled imagery layer and a dynamic imagery layer. So comparing the two layers, I'll just jump to the next slide. So compared to the traditional tiled layer, the two new imagery layer types have many advantages. The traditional tiled layer can only serve static tiles, which are 1 or 3 band JPEG PNG files, commonly used as a base map layer for fast visualization, but have obvious limitations. In contrast, the two new tiled imagery layers can also support the images with more than 3 bands and even multi-dimensional raster data, which makes it fast visualization and also suitable for analysis. Although if you need additional functionality such as server-side on-the-fly image processing and dynamic mosaicing of image collections, then you need to consider a dynamic imagery layer. Dynamic imagery provides powerful server-side processing capabilities and puts less load on the client. Existing tiled imagery layers can also be republished as dynamic imagery layers for additional functionalities if you need. So now I'll jump into the demo and show you how to upload and configure your imagery files into ArcGIS Image for ArcGIS Online. So once you have decided on if you would like to import tiled or dynamic imagery, you need to configure your layer. You can choose one, there are 4 different ways you can configure your data. You can choose one image, which simply will upload one file as a single imagery layer. One mosaic image, which will upload multiple image files and automatically mosaic them into one imagery layer. An image collection will mosaic the image files into one layer, but will maintain access to each image independently. Or you can create one imagery layer for each file you upload if you choose the multiple imagery layer option. Next, you'll choose your product definition. You can upload common image file formats using the raster dataset option. Upload scientific file formats such as GRIB or NetCDF to these support multi-dimensional rasters. Or alternatively, you can choose from one of the 30 different product definition templates. These read your imagery associated metadata. Now browse to your imagery or simply drag and drop the files into the window below. Once you've finished uploading, you need to then add some item details and click Create. If your imagery has been uploaded as an image collection, you'll have the image management menu appear, allowing you to perform further calculations on the layers, such as building footprints, calculating statistics, and defining no data values. For all other dynamic imagery layers, in the settings menu, you have access to additional settings such as requesting pixel limits and defining raster data functions for default rendering templates. You can view the imagery in the new map viewer, and once you click Save, you can view the imagery in the new map viewer and quickly switch between the preset rendering templates. You can then share this layer with your colleagues, and they'll be able to use the raster function template viewer to visualize the layer in different ways without having to run the raster functions themselves. And so that was just a quick introduction of publishing data into ArcGIS Image for ArcGIS Online. And so now I'll jump to James to show you some examples of how you can analyze that imagery that you have now uploaded. Cheers.
Awesome. Cheers, Phil, for that. That was a really great intro to ArcGIS Online imagery. I'll touch on some of the other analysis capabilities of ArcGIS Online imagery as well in the following demos. But jumping to the next slide, as Baldovan mentioned earlier in the webinar, the ArcGIS system has a wide array of imagery analysis tools available to us. I'll be focusing on a few of these capabilities. However, it's really good to understand, I guess, the breadth of imagery analysis capability within the platform. The next slide, when it comes to, I guess, raster analytics in ArcGIS, it's important to understand the different mechanisms you can leverage in your analysis. Analytic tools are available across desktop in ArcGIS Pro, over the web by ArcGIS Enterprise, and now ArcGIS Online as well as tools being made available through the Python API. Across all of these scenarios, analytics can be run on image sources that are either local, on a shared drive, or as an image service like in ArcGIS Online. What platform you use really depends on a number of factors, such as the type of tool, the complexity of the workflow, scalability of your tasks, or the ability for customization, to name just a few. But there is likely an interface that will suit your use case. So just have a look at each of those. On the next slide, deep learning is a type of imagery analysis that is gaining more and more traction as the tools become more accessible and easy to use. In ArcGIS Pro, there are a number of tools that allow you to utilize deep learning, such as pixel and image classification. This analysis can be run on all types of imagery sources too, such as satellite or bathymetry data, to 3D sources such as LiDAR, oriented imagery, or even motion imagery. ArcGIS provides the framework and interface to perform your deep learning tasks, but they actually rely on third-party deep learning framework libraries. These frameworks vary in the way that the data is trained, as well as the type of tasks you can complete with them, with some excelling at things such as object detection, for example. If all that seems a bit overwhelming to you, then hopefully my next slide should help you out. Now, ArcGIS provides you with that complete interface to perform your deep learning workflow, starting with the ability to manage all of that imagery ready for analysis, as well as the interface and the tools to complete that data labeling, data preparation, and the training of the model. Finally, to the inferencing, performing analysis, and providing tools to serve out your analysis through web applications, dashboards, as well as field applications. Coming up, we'll have Plant Tech Research taking us through a similar workflow with real-world outcomes. Now, Esri is helping us out with the most time-consuming steps of data labeling, prep, and training that model by providing pre-trained deep learning models. This allows us to simply run data we have directly through those models and hopefully gain actionable results directly from it. In the next slide, I have an example of the over 20 pre-trained models ready to use ready for you to use out of the box. You can find them by searching for deep learning packages in the Living Atlas. If there's a video, there we go. There's new models to extract windows and doors from 3D meshes, classifying trees and power lines from LiDAR, as well as road extraction from imagery or object tracking in videos, for example. So head online and check those out when you get a chance. Now to a quick demo of utilizing raster functions and raster analytics using ArcGIS Online and Pro. Cool. So I want to quickly start off here in ArcGIS Online. I have here a DEM created from the recent 1 meter LiDAR for the Westport area. The layer is hosted as a dynamic imagery layer by ArcGIS Online. Now I want to perform some analysis on this layer. So I'm going to fire up ArcGIS Pro. Here I can access my content from ArcGIS Online. I'm going to directly add that dynamic imagery layer to my map. I now want to apply some raster functions to this elevation layer. Like I mentioned before, raster functions are great for applying on-the-fly processing to your imagery layers. Here I can apply one of the over 160 different tools available to me. And as mentioned, you can chain multiple raster functions together to create what's called a raster function template. Here I want to calculate flat to steep areas. And I'll use a raster function chain to calculate the slope, remap it into certain slope bands, and finally color and name the outputs. As you can see, the rendering applies almost instantly using client-side rendering. Now, if I wanted to create a permanent layer from this, I can go ahead and run a geoprocessing tool. These raster function templates can be shared amongst your organization or publicly. With ArcGIS Image for ArcGIS Online, I can now apply these raster function templates directly to dynamic image layers from the map viewer. Here in the map viewer, I have the same Westport DEM dynamic imagery layer. Under analysis, I have the access to raster analysis tools. Here I can see the raster function template that I just published. And my colleague Phil has already created a raster function template that analyzes my layer for low-lying areas. Here I can select whether I want a tiled or dynamic imagery layer, further analysis, and I'll select a dynamic imagery layer. I'll go ahead and run that and view the resulting layer. This tool has quickly enabled me to identify low-lying areas and even the individual pixel values. The raster function template can now be applied to new data as it becomes available. Having the ability to host imagery layers that are ready to use for analysis inside ArcGIS Online is great by itself. However, coupling that with the ability to run raster function templates for common imagery analysis workflows within an organization really opens up a whole range of possibilities going forward. For example, having burn index raster functions ready to go whenever you receive new imagery in the case of emergency, or for flood risk like shown here. The list really goes on. But for now, it's time to hand back over to Baldwin. Actually, no, we're going to Plant Tech Research, who's going to take us through a more in-depth analysis, imagery analysis workflow. Thanks.
Welcome everyone. My name is István and I am one of the research scientists at Plant Tech. We are extremely pleased to be part of today's event and very happy to share some of our work in this exciting session. Me and later on my colleague Mohamed will talk about how we use remote sensing to map foliar nutrient content in kiwi fruit orchards. This work and its future directions is guided and led by Ian Yule, our research director. Just before we go into the details, I'd like to take the opportunity to briefly introduce our organization, since Plant Tech has only been around for a few years. Plant Tech is an industry-led regional research institute based in Tauranga, and its initial investment was secured by MBIE. Then it was founded by a partnership of horticulture-aligned shareholders in 2017. We address challenges dominantly in the horticulture industry by applying science and cutting-edge analytics, including artificial intelligence. We are a bunch of research and principal scientists spanning over backgrounds in data science, mathematics, computer engineering, computer vision, precision agriculture, bioinformatics, GIS, and remote sensing. The science team is supported by senior management members to make sure that our projects are progressing efficiently and made visible to the wider community. We are all excited about data and the possibilities that we can leverage to support technological innovation in plant-based value chains. As location is a key component of most of our datasets, we've been developing experience and capabilities in the interface of remote sensing, GIS, and AI to reveal patterns that haven't been seen before. In terms of remote sensing, we have been investigating the capabilities of a wide range of products, including publicly available datasets, commercial spaceborne and airborne imagery, as well as terrestrial and airborne LiDAR data. This chart depicts a comparison of these products as a function of temporal, spatial, and spectral resolution, alongside with an indication of their cost. Since we work across various geographic scales, each of these products and techniques has advantages and disadvantages depending on the task in hand. Today, we will focus on two fairly different members of this list and the associated foliar nutrient analysis work. Hyperspectral imagery, shown by the large red spot, provides an incredible amount of information captured by hundreds of spectral bands or channels and offer high accuracy when it comes to deriving plant-related attributes. It is a rather expensive approach, and surveys will be completed only a few times a year. On the other hand, Planet's SkySat products are considered low cost and can offer daily image captures. It can also extend the spatial scale. However, a compromise will need to be made in terms of spectral resolution and the predictive ability. First of all, why do we want to know nutrient levels, specifically nitrogen, of the plants? We know that nitrogen is an essential macronutrient, and its status has a proven effect on plant performance, productivity, yield, and deficiencies can limit growth. Besides, growers often apply fertilizers in excess to avoid any risk of yield reduction, which has resulted in undesirable environmental impacts. Spatial foliar nutrient analysis is a relatively new approach that was made possible by the advancement of GIS and remote sensing techniques. Foliar analysis can offer a reliable assessment of nitrogen levels in the leaves, which can inform fertilizer application planning to match crop demand. Below is the typical kiwi fruit development cycle, and we can see that based on the timing of nitrogen level analysis, useful information can be acquired for management. Early diagnosis of nutrient deficiencies can drive input planning, while an assessment during the fruit development phase can provide an understanding of the fertilizer program efficiency. Furthermore, nitrogen levels in the late season can be linked to finer fruit quality and yield metrics, as well as orchard returns. It is obvious that there are significant benefits to track nitrogen and other macro and micronutrients. This is a visual summary of our nutrient mapping work, a graphical abstract, if you will. On the left, we can see our data sources, which is a set of nutrient levels derived from wet chemistry of leaf samples, and a collection of hyperspectral and multispectral images captured at the time of the ground sampling. We feed this dataset into an AI-driven data science workflow, which outputs spatial layers of nutrients. To convert the resulting layers to actionable, easily digestible information, we apply a set of GIS tools, geospatial analytics, and dashboards. We believe that the information generated by the combination of data science and spatial techniques is able to support orchardists' decision-making to achieve optimized fertilizer applications, enhance productivity, as well as mitigate the degrading environmental effects. To collect run-throughs, we sampled 12 orchards at 15 sampling sites and repeated this 3 times during the last growing season. The orchard displayed here is located somewhere in the Bay of Plenty, and if you pay attention to the levels of nitrogen represented by those colored columns, you can see how the levels change over time and spatially. This insight confirmed the idea of foliar nutrient mapping, since there is spatial and temporal variability that can affect orchard performance. Before moving on to the image collection methods, I will briefly explain why multispectral and hyperspectral imagery is useful for vegetation monitoring. I've extracted spectral signatures for common targets on the land surface, such as kiwi fruit canopy, an avocado tree canopy, a building, and road surface. By exploring the signatures from a 3-band RGB image, we can already see that these features have different spectral behavior. However, looking at the same targets through a multispectral sensor, we are starting to notice patterns which are well represented in the near-infrared domain of the electromagnetic spectrum. Let's have a look at the targets through a hyperspectral camera. We can see that these surfaces have distinctive curves that are also reflected by the shortwave infrared domain. While RGB images can provide useful information, using the power of multispectral and hyperspectral cameras, we are able to detect a broad range of vegetation characteristics reliably and very accurately. And now, I will pass the time to Mohammed to explain our image collection methods and share processing steps and the results. I'll be back for a few more minutes with a quick demo on how we envisioned the delivery of these spatial information layers to growers and end users. Mohammed, over to you.
Thank you very much, Istvan. As my colleague introduced me a bit earlier, my name is Mohammed, and I work quite a bit with the hyperspectral and multispectral data we have at Plantech. And in this section of the presentation, I will go through some of the results we have achieved using hyperspectral and multispectral data for predicting canopy nitrogen concentration of kiwi fruit. After that, I will hand over back the presentation to Istvan, who will show you some exciting stuff. We are working very closely with partners at Palm in Hyperceptions and a company based in Palmerston North in order to capture high-quality hyperspectral imagery. The hyperspectral imagery is pre-processed at Plantech, and we are provided by processed hyperspectral data, which we'll use to create our datasets and models to predict nitrogen concentration of kiwi fruit canopy. In addition, we work very closely with our partners at Eagle Technologies to acquire SkySat imagery. SkySat is a very high-resolution, spaceborne instrument which captures 4 bands in the visible near-infrared region. One of the key benefits of SkySat is that it captures imagery at a daily or sub-daily basis, which is quite important, as one of the key disadvantages of hyperspectral imagery is the fact that it is temporally coarse. At Plantech, we have built the capacity to process high volumes of data rapidly, using parallel processing and GPU computing. In addition, we have expertise in a range of data analytics techniques, ranging from genetic programming, deep learning, machine learning, statistical modeling, and so on. In addition, we are building capacity in order to do physical modeling of biophysical and biochemical characteristics of the kiwi fruit canopy using radiative transfer modeling. As seen in this slide, we are able to use hyperspectral imagery in order to predict nitrogen concentration of kiwi fruit canopy very accurately. With an R-squared of almost 0.9 and a mean squared error which is quite small, we are able to predict nitrogen concentration at a regional level very well. In addition, we are hoping to relate the nitrogen concentration of the foliage of kiwi fruit to fruit quality and yield in the near future. In addition, we are planning to relate fruit quality and yield information in order to develop profitability maps very soon. We are using the SkySat imagery in order to have an understanding of what is the capacity of the sensor in order to predict nitrogen concentration of kiwi fruit canopy. As seen in the scatter plot here, although the performance of despite as the number of bands is quite limited in comparison to the hyperspectral data, still there is a reasonable relationship between the 4-band instrument and nitrogen concentration of the canopy. This is due to the fact that there is a strong relationship between the red region of the spectrum and chlorophyll concentration of the vegetation. Although the performance is not as good as the hyperspectral data, this model allows us to discriminate between low, medium, high concentration of nitrogen in kiwi fruit orchards. This can be confirmed by looking at the KDE plot below, as it shows a very strong similarity between the actual nitrogen concentration and predicted nitrogen content. By using SkySat imagery, we are capable of monitoring nitrogen concentration at a very large region, and due to the high spatial resolution of the instrument, we can see clear differences within blocks in orchards. We can understand what is happening at a regional scale, and we are hoping to actually understand if we are hoping to recreate this at a national scale very soon, in order to understand which blocks are high performing and which are low performing, in order to provide useful information to the grower. In the next slide, my colleague will present some of the exciting stuff we have been doing regarding dashboarding and visualization.
Thank you, Mohammed. An interactive dashboard can be a suitable way to provide a platform to integrate management, history, real-time weather, and remote sensing-based nutrient information. As we were talking to several growers, this highly visual, traffic light-like solution was received very well. I will guide you through the main functions of this dashboard that completes the story of today's presentation. On the top left, we have a list that contains a repository of management activities and their timing per block. Just below that, we have a weather and soil monitoring section receiving live data streams from IoT sensors and the local weather station. Since the timing of fertilizer applications is critical for a successful high-yield season, time series of soil moisture, soil temperature, and air temperature are plotted. The major component of this dashboard is the satellite data-driven widgets that take in the extracted nutrient information from multiple image captures. In the bottom, potassium, phosphorus, and nitrogen levels are displayed in a form of gauges and time series plots. A full list of blocks is presented on the top right that can be used to rank the blocks or track nitrogen levels over time. We have also identified management zones considering high, optimum, and low nutrient ranges. This way, we can highlight areas that require attention and a potential change in management or the amount of fertilizer applied. As an additional feature, we can go beyond the block scale and get an understanding of the nitrogen levels in individual bays. Using the same nitrogen value ranges, we can identify the problematic areas which might provide another source of information in a more detailed manner. With that, we have arrived at the end of our presentation. And to wrap it up, I'm coming back to our graphical abstract. In the last 15 minutes, we have demonstrated our nutrient mapping workflow from the very beginning, starting with a proof of concept, data collection, and then we moved on to sharing details about model performance and data analysis. We also explained to you that the chosen imagery sources have their limitations, which is an important factor to be aware of. And lastly, by creating a GIS-driven dashboard, we managed to reshape the output of a complex workflow into actionable information. We are going to keep working hard to improve our models and eventually create an operational, industry-wide product. We have to realize that the development of geospatial tools, AI, the increasingly available computational power, and the new era of remote sensing are changing the ways we see and monitor the landscape. There is a lot more to explore. Finally, we would like to say thank you for your attention, and we wish to thank Eagle Technology for their support during the process of establishing Plantex GIS systems, as well as for the opportunity to be here today. We would also like to acknowledge the work of Planet, HiPerceptions, and Interpine for providing imagery. If you are interested in this work or some of our other projects, please get in touch. We are always happy to chat and discuss potential areas where we can work together. Please go and visit our website, where you can read about case studies and find frequent updates on Plantex activities. Enjoy the rest of your day.
Yeah, thanks Istvan and Mohammed for this story. And it's a great example of how much information can be hidden in imagery, but also how it can be presented in a friendly way for the end users. So with that, we've come to the end of the content of our stream session, and we hope to have given you an overview of ArcGIS Image and the different capabilities. But for sure, the customer stories will have inspired you to look at imagery as a source of information. We've talked about many topics during this presentation, and we have collated some resources that can get you started or give you more information. And this document will be sent to you after the session, including answers to the Q&A. Also, we like to announce an ArcGIS NZ Elevation competition. And this is something that will start where you can tell us about how you're using ArcGIS and the New Zealand LiDAR together, and what real world problems you're trying to solve and how you use innovative solutions for that. And you can participate by creating a story map to tell about your work and then send it to us at nzeuc@eagle.co.nz. So you've got some time as well, because we will close the submissions by 28 February 2022. Please see the social media channels or our blog page for prizes and more information. If you have missed any of the previous streams or want to watch the NZEUC plenary, just go to the Eagle Technology YouTube channel where you find the recordings. We'll also have one final live stream session this Thursday on Field Apps in ArcGIS, so make sure to register and tune in for that one. Then now we are moving to the Q&A, and James will guide us through the Q&A. If we can't touch on all the questions, we will be sure to follow up with you on the questions that you have asked us. So James, over to you.
Yeah, sweet. Thanks, Peter. Then I'm conscious we're over time, so yeah, if you want to hang around for Q&A, please feel free. Well, maybe I'll jump in now while we sort out the microphone issues. We had a couple of questions around full motion video and oriented imagery as well. And then there's a couple of questions around, can we use drones videos to, I guess, view that video in ArcGIS Pro? And the short answer is yes, you can. You can you can use the ArcGIS SiteScan Flight, which is that mobile planning tool, along with your drone to fly your drone, capture some video, and then bring in all the relevant metadata you need to extract information and view that video in a georeferenced fashion. In terms of, there's a question around 360 video as well. So what if you're capturing terrestrial 360 video? Then it's definitely worth looking at the oriented imagery extension or tool. Oh, I can hear someone now. I think like Mohammed. If you want to, I can ask that question then. What are the steps required to taking your data set nationwide? Sorry about the technical issues.
Can you hear me?
Yes, yeah, there we go.
Awesome. Regarding the updating the data set, I think the key is to actually create a data set which has a large amount of variability within. At the moment, our majority of the focus that we had was in the Bay of Plenty, so mainly in Katikati and Opotiki and Te Puke. So the question would be, if we actually manage to make a data set that captures all the microclimate and climatic information across New Zealand, we can actually make a model that is quite generalizable and can be applied to the different the SkySat imagery. So we are also looking at kind of improving the performance of the SkySat imagery by using deep learning, so image fusion, and trying to increase the amount of the quantification ability of the SkySat imagery. So it requires on quite a bit of data and deep learning type of approach to improve the performance.
No, that's awesome. Thanks for that answer, Mohammed. And actually, while I've got you, I've got another question for you. What were some of the purely in ArcGIS webinar? Were you using any of the ArcGIS tools for image management or any of your deep learning steps?
So I use a lot of for the image object detection and that type of work, we use ArcGIS quite a lot because of the pre-trained models are quite useful. So it enables us to kind of do demos or initial analysis very quickly. And after reaching initial model and getting the initial results, we try to move that to a lower level language or using Python code to do the analysis. And we move it back to ArcGIS to do the further visualization work.
Oh, awesome. Yeah, those dashboards at the end are looking fantastic, by the way. It's
Oh,
really
that is absolutely Ishtvan's magic.
Yeah, it looks like a really usable interface to get really complex data into a nice visual form, right?
Absolutely.
Yeah, I really appreciate you guys coming on the webinar this afternoon. And yeah, if you want any more resources from Plant Tech, we'll be sending out documents as well as checking out their website.
Thank you so much. Thank you.
Thanks, guys. I've got a question for Maurice from ECAN as well. If you're on the line, how is ECAN looking to host all their imagery in the future, and what tools are you looking at to do that?
Yeah. Hi, James. Can you guys hear me okay?
Yep, yeah, I can hear you.
Yeah, so moving more and more into serverless technologies, so getting up the imagery into ArcGIS Online. Certainly we've got a project going on at the moment to move. We've got the historic imagery across, and we're just working through our latest imagery, and the cache for the latest imagery stuff is quite large, over 1 terabyte, so we're just working through some of those issues. We've had a play around with ArcGIS Image early on, but yeah, we want to get back into trialing some of that ArcGIS Online image extension, and then obviously, you know, Kubernetes and other things are on the horizon. So just being flexible in terms of we want to be able to serve the imagery up quickly for everyone, and then getting out of the processing, you know, the time it takes to process the imagery, because we want to get into the analysis and the use of the imagery more than the preparation of it.
Yeah, that definitely makes sense. Hopefully freeing up more time for yourselves to do more important work. Well, not more important, but useful work.
More high value work, yeah.
Yeah, exactly. That's awesome. We really appreciate the presentation you put together for us today as well. And if you've got any more questions for Maurice, please fire them through, and we'll try to get them to him afterwards as well, even if we haven't got them quite now. But yeah, really appreciate your time. Thank you. I don't know if we've got many more questions, but maybe one for our team, maybe Phil or Balderbane or Ted even. How can one access ArcGIS Image for ArcGIS Online? What are the processes involved there?
I'm happy to jump on that one, James, or Balderbane.
No, you go ahead. You go ahead.
Okay. Sure thing. ArcGIS Image is an extension for ArcGIS Online, so you can add it on to a subscription if you either have an online creator user or an ArcGIS desktop license if you're a GIS professional user. So it's compatible with those two user types. Yeah, and it'll just be an uplift on your current subscription. So yeah, if you are interested in adding that on, please just get in touch with us at Eagle, or if you know who your account manager is, just go direct to them. And they can help you out.
Thanks, Ted. Cool. I'm conscious we're well over time now. I can't see too many more questions coming through. There's a couple more we need to do a little more research on. We'll get back to you in that research document, the resource document following this web presentation. Yeah, like we said, there's the recording will be available on YouTube following the conclusion of this, as well as that resource document, as well as the PDF document of these slides. We had a few questions about that, and we can make those available to you. But yeah, back to you, Balderbane, if you've got any closing comments. But from me, thanks very much for coming along.
No, all I have to say is that I want to thank everyone for joining this session, and please reach out to us or any of the presenters that you've seen if you've got any questions. We are happy to relay any questions that you have for any of the presenters, so you can fire them through to us as well. For now, I just wish you a good rest of your day. I would love to have lunch together now. Unfortunately, we can't do that now, but maybe next year. But thanks again for watching, and we'll see you next year, hopefully.
Cool. Cheers, guys.
Thanks very much, everyone.